So today's lesson is on 7.4, applying properties of similar triangles. So before we get started, the math humor for today says, what do you call two L's? The answer is a parallel, like a pair of L's. Get it? Ba-dum-bum. So we're going to take a look at the notes. And the first thing we're going to deal with in the notes today is the triangle proportionality theorem, or otherwise known as my TP theorem. I like to think about it as the TP theorem. And what this theorem states is, if a line is parallel to one side of a triangle and it intersects the other two sides in two distinct points, then it actually separates these two sides into segments of proportional lengths. What it really is saying that if my BD is parallel to AE, which is a side of a triangle, then BD is going to split the side AC and the side CE into proportional measurements, meaning that the segment CB compared to BA would be exactly the same ratio as CD compared to DE. It's almost like we're working down the sides here. So we're going to apply our triangle proportionality theorem, or our TP theorem, to the following problems. So for the first example, if I take a look, I notice that I do have a parallel line segment inside of my triangle, and it's parallel to one of the sides of the triangle. Once I see this, and if all the information is on the sides of the triangle, or two sides of the triangle, then I know I can apply the TP theorem, the triangle proportionality theorem. And the triangle proportionality theorem goes as such. We're going to take 2 and put it over x. So 2 compared to x would be the same exact thing as having 3 compared to 6. All I'm doing is working down the sides of the triangle. Now, since you've got this set up, we cross multiply. So the x times the 3 gives me 3x. The 6 times the 2 gives me 12. And if I solve, I end up getting x is 4. So if I take a look at the next one in part B here, I notice that I'm working with the triangle. And in this triangle, I've got a parallel line segment to this one. But my problem is this is actually a different example than the one we dealt with in A. In A, all of my information were on the sides of the triangle. In this case, though, I don't have all of the information listed on the two sides of the triangle. I actually have information listed on one of the sides of the big triangle and this one down here, but I was really hoping to have something over here. If I did have information labeled over here, I could use the TP theorem. But since I do not, then I have to look at this as like a little triangle compared to a big triangle. Okay, so we're actually going to compare our two similar figures. And before I do that, what I would like to do is maybe draw them out separately. So I'm going to draw out the little triangle, and then I'm going to draw out the big triangle. So on my little triangle, let's talk about this. On my little triangle, I know two sides of my little triangle. I know I've got a side of 4, so we're going to put that there, and I've got a side of 10, and we'll put that there. So I've got 4, and I have 10. Then, here's the tricky part. When I take a look at the big triangle, I do have the sides. This whole side in my big triangle is 10. We'll write that. And then this whole side in my big triangle is x. So now I've got two similar figures, and with these similar figures I can still set up the ratios. So we're going to say 4 in this triangle compares to 10 in this triangle, just like 10 in the smaller triangle compares to x in the bigger triangle. So there we go. 4 over 10 equals 10 over x. Now all I have to do is cross multiply, so I get 4x equals 100, and x is 25. So it was all because the information didn't lie on the two sides of the triangle. We could not use the TP theorem. We had to use a little triangle, big triangle theorem. So biggest thing is, if you ever have information in the middle of your triangle, do little triangle, big triangle. Otherwise, if all the information is lined up on the sides of the triangle and nothing's on the inside, then do the TP theorem. So for part C, I'll ask my students, TP or no TP? That means, do you do the triangle proportionality theorem, or do you do a little triangle, big triangle? Well, do I have any information labeled on the parallel line segments? If I don't have anything labeled in the middle here, I know I'm going to do TP. All the information is labeled on the sides of my triangle. So my TP theorem says, let's go ahead and start off, because we're going to work down one side at a time. So I would do x plus 6 over x. So that took care of x plus 6 over x, and then I would compare it to this amount over 9. Now you might be saying, well, this is missing. Yeah, it's missing. However, you do know the whole entire side length is 30, and this is 9, so I would take 30 minus 9, and that would give me a side length of 21. So now comparing, I would say it is 21 over 9. Now all we do is cross multiply and solve. So when I cross multiply, I get 9x plus 54 equals 21x. I'll subtract 9x from both sides, so I get 54 equals 12x, and then from this point, all you have to do is just divide both sides by 12. And when I divide by 12, I will get 4.5. Now remember from first semester, converse of a theorem just means you switch the if and the then. So the converse of the triangle proportionality theorem says that if a line divides two sides of a triangle proportionally, then we know that line would be parallel to our third. So in our instance, if we know that CB over BA would be the same thing as CD over DE, then I can prove that BD would be parallel to AE. So in our example here, we're going to take a look. If I can show that 10 over 15 equals 8 over 12, then I know that this line is parallel to this line. And we're just going to quickly show that and make sure that that is true. So 10 over, let's go ahead and erase that. Let's do this again. 10 over 15 equals 8 over 12. So if I go ahead and I cross multiply my quantities, I will end up getting 120 for the 10 times 12 and 120 for 8 times 15. So since I knew the proportion was the same, I ended up getting 2 parallel lines. So what happens if you're dealing with 3 or more parallel lines and they intersect 2 transversals? Like all you do in this diagram, I have 1, 2, 3 parallel lines and they're intersecting 2 transversals. Then what happens is we know that if any of that occurs with parallel lines, those parallel lines and the transversals, they actually cut the transversals proportionally. So that means that DE over EF would be the same thing as AB over BC. It's kind of like the TP theorem, but instead, I'm not necessarily dealing with a triangle. I'm dealing with parallel line segments more than anything else. The other corollary we have here says that if 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So if I knew my parallel lines here, AD, BE, and CF, if they cut it off such that DE was congruent to EF, it does it in a manner that AB would be congruent to BC. Now, the DE doesn't have to be the same thing as AB, but if these two are congruent, then I automatically know that the 2 on my other transversal should also be congruent. So for this example, we're going to use that corollary we just talked about, and it says, suppose that an artist decided to make a larger sketch of the trees. In the figure, if AB is 4.5, BC is 2.6, and CD is 4.1, along with KL being 4.9 inches, we are going to find LM and MN to the nearest tenth of an inch. So I noticed that we've got trees, and we're going to assume that these trees are all straight, so that means they're all going to be parallel. AK, BL, CM, and DN are all parallel lines, and they're intersecting our 2 transversals. So when that happens, we know that the proportions that we end up getting are going to be the same. So I am going to set it up, and I will say, working down one side, I'll say that AB over BC should be the same thing as KL over LM. That's going to help me solve for LM first. So AB was 4.5, BC was 2.6. That'll equal 4.9, which was our KL, over my LM, which I don't know. So now all you have to do is cross multiply and solve. How about you pause the video, do it yourself, come back when you're ready, and I'll have an answer written down for you. All right, so after you've done your cross multiplication, I did 4.5 times LM, and then I did 2.6 times the 4.9, got my answer there, and then divided both sides by 4.5. I ended up getting a 2.8311-ish. So then what happened was, if I'm rounding to the nearest tenth, I would say it's 2.8 inches. How about you go ahead and set up the next equation so that you can go ahead and solve for MN. So now when I'm taking a look at setting up my equation, I'm trying my hardest not to use the measurement for LM because LM is indeed a rounded value. So if I can try to not use it, we're better off. So let's go back, and I'm going to suggest we use AB and CD this time, and we'll compare it to KL and MN. So the setup that I'll use will be 4.5 over 4.1, because that's AB over CD, and we'll set that equal to 4.9 over MN. So when I cross multiply here, 4.5 MN will equal, I got a handy dandy calculator here, 4.1 times my 4.9, just to make sure I've got it right. We get 20.09, and we're going to divide that by 4.5. So my answer that I get for MN is 4.464, but if I round it to the nearest tenth, it will be 4.5 inches. And the last theorem of the day has to do with the triangle angle bisector theorem. And it says that if you are working in a triangle and you have a segment from a vertex to the opposite side, that ends up bisecting the vertex angles, so that I get angle BAD congruent to angle CAD, it does such in a manner that BD compared to DC, it would be the same as AB compared to AC, so that proportion is true. If we use this theorem on the following two problems, we can solve for x. So we know we've got an angle bisector inside, so that means let's go ahead and start off with 6. So if I started off with 6, I would compare it to x, and it would equal, go back to the other side, 9 compared to 12. So 6 over x equals 9 over 12. And if I cross multiply, I'm going to get 9x equals 72, and we divide, we'll end up getting x equals 8. How about you go ahead and try the other one on your own, pause the video, and when you're set and ready, I'll have the answer written down for you so you can double check. All right, so we're going to take a look at this one, and I said I was going to have the answer written down, but I figured going through it, it would be a little bit easier if you saw it. So I've got 4.5 compared to the x over 2 is equal to 8 over the x minus 2. Now when I cross multiply, I have this 4.5, and it's times x minus 2. So I'm going to have to distribute my 4.5 through. And I'm running out of room. That's why I'm talking you through it rather than writing all my steps down. You should probably write all of your steps down if you're doing this on your own. So I'd have 4.5x minus 9, because I had to distribute my 4.5 through. And then, this is a little trickier, I get 8 times x over 2. Now x over 2 is the same thing as a half x. And 1/2 x times 8 gives me 4x. Now that I have this, I'm going to go ahead, and I feel comfortable if I subtract my 4.5x from both sides. I'll get a negative 9 equals a negative 0.5x. Well, that's looking horrible. Oh, we're going to deal with it, though. Negative point, we're going to write it over here. Negative 9 equals a negative 0.5x, and then we'll go ahead and divide by a negative 0.5. If you didn't like that, you could actually subtract 4x from both sides and then add 9. When I do this, these will cancel. I'm left with x equals, and negative 9 divided by a negative 0.5 becomes a positive 18. So that's what we end up getting for that one. So you have several theorems you have to know, the TP theorem, triangle angle bisector theorem, a couple corollaries to keep in mind. If you have any questions, make sure you ask in class. Otherwise, have a great night.